Good afternoon. My name is Susan Margulies, and I'm the Assistant Director for Engineering. We're delighted to welcome you to this public lecture by the NSF Waterman awardee, Dr. Asegun Henry. The Alan T. Waterman Award is NSF's highest honor that recognizes an outstanding early career researcher, and it comes with $1 million for research and education at their discretion. Dr. Henry is a professor at the Massachusetts Institute of Technology, where he directs the Atomistic Simulation and Energy Research Group. He's also the founder and CEO of Thermal Battery Corporation, an MIT spinout commercializing low-cost, grid-scale, rechargeable battery technology. Prior to joining MIT in 2018, Dr. Henry was an assistant professor in the Woodruff School of Mechanical Engineering at Georgia Institute of Technology. Professor Henry is also the recipient of a number of awards, including the NSF Early Career Development Program, which is a career award, and the 2021 Nokia Bell Labs Award, as well as the 2018 World Technology Award for Energy. Dr. Henry's Waterman Award recognizes his significant contributions to new energy technologies and advanced fundamental understanding of heat transfer, addressing a broad range of problems. The implications of his research span from the atomic scale through a better understanding of the physics of heat to the gigawatt scale by introducing new options for grid-level energy storage. Put simply, Professor Henry has made the impossible possible. His revolutionary approaches are advancing the fields of heat transfer and energy storage with an ultimate goal of mitigating climate change and benefiting the future of humankind. Today, Dr. Henry will address rethinking problems of thermal science and engineering from atoms to applications. Dr. Henry, congratulations on your Waterman Award, and we're glad that you're joining us today, and we look forward to hearing your remarks. Thank you.
Thank you. Thank you for the wonderful introduction. Let me share my slides. Let me know if this comes up okay. Is everything showing up fine? All right, great. All right, I will, the title of my talk, Rethinking Problems in Thermal Science and Engineering, is really based on a theme that has grown or shown up in a lot of the research I've done. It's interesting to kind of reflect on where this theme really came from, and I, in a sense, dedicate this award and this talk to the many people who helped mentor me as I was growing up as a kid. In particular, I was in a manhood training program, a rites of passage program when I was young, and one of the most important things that I got out of that, which actually spurred my interest in becoming a scientist and engineer, was this idea of really questioning all the things that you've been told as a kid growing up. Everything you learn is essentially just what people tell you. And in this program, we were taught to think for ourselves. And that idea that we should think for ourselves really pervaded how I approach science, how I approach engineering. And this theme has really cropped up in a lot of my work, where my preference, strong preference, whenever I encounter a new problem, is really to rethink it from scratch. I like to start from the beginning. Unlike many researchers, I don't like to read papers first. I actually like to start the problem on my own, figure out whatever it is I think, and then I'll go see what everyone else thinks after that. And that has really informed my approach. And as I'll show you through the talk today, which really covers more than a decade of work, has really informed how I've approached things. And you'll see that there's a number of opportunities that we've identified where we are able to advance the field in some significant way by really rethinking things from the beginning. And so I'll show you a number of examples of that. There's at a high level, there are two main topical areas that I work in. The first is maybe best labeled as my bread and butter, so to speak, what it is that I did coming out of my PhD work back at MIT when I was a graduate student, which is the study of the physics of atomic vibration and how that relates to or manifests as heat transfer at the atomic level. I will talk about this plot on the left. It looks kind of very generic, but I'll talk on the next slide or two about what that really means. The second area that I work in very broadly could be titled as just high temperature energy systems. There is a particular technology that we've been developing for the last decade, which has been referred to as sun in a box, or we now call it thermal batteries. And that's the name of the company that I founded. I'm now CTO of Thermal Battery. So I'll talk you through that technology. And there's actually a second technology we're also developing in my lab, which is related to the core innovation, which is the infrastructure, the ability to pump liquid metal at extreme temperatures using an all graphite plumbing network. These are the two main areas that I work in, and very excited to share with you some of the things that we've developed. So the first area that I want to talk about with atomic vibration, I need to maybe spend just a second to describe this notion of a phonon, because I'll keep talking and referring to this term phonon. So let me just say briefly what a phonon actually is. Everything in the universe, our bodies, everything is made out of atoms. When you talk about, let's just maybe restrict ourselves to talking about solids. In solids, the atoms are constantly vibrating around some local site. They're not translating or moving throughout matter. They are in space. They are actually localized to one location, and they're vibrating. Those vibrations ultimately come from the interactions of the atoms that are surrounding them. And those vibrations can actually be decomposed into a addition of lots of different individuals, so to speak, sine wave vibrations that are at different frequencies. And there's a whole spectrum of frequencies that are active at a given time. And from quantum mechanics, it turns out that these different frequencies, these different oscillations actually have quantized amplitudes. And in the same way that there is a wave-particle duality for photons, in the sense that the electromagnetic field has quantized amplitudes, the same is true for the vibrations of atoms. They also have quantized amplitudes, and we call those jumps in amplitude, we call them phonons, by analogy or by relationship to photons. The distinction with a phonon, of course, it has energy h bar omega. It's got some wavelength as long as the vibration looks like a sine wave. It's got a speed. There's a phase speed. There's a group velocity. And the basic physical picture associated with these phonons, which are now envisioned to be like particles that are traveling and carrying energy from one location to the other, that's the basic physical picture of how heat transfer happens in the quantum realm. The basic physical picture and the basic description that describes how this heat transfer happens is something we call the phonon gas model, or the PGM, as I'll abbreviate. And the way that essentially all the expressions that are based on the phonon gas model start is they, by analogy, treat the energy associated with the phonon the same way you would treat a gas particle. So a gas particle moves, it carries with it its kinetic energy, and this is the foundation of kinetic theory, where you can derive all the properties of gases. And so if you treat phonons like a gas, like they're bouncing around at different speeds, you can then derive the properties associated with phonons, such as things like thermal conductivity. And so the key thing is that you make this analogy where you treat the energy of a phonon, whereas the same like you would have treated the energy of a gas particle. Here it's the kinetic energy, 1/2 mv squared. For a phonon, it would be h bar omega, the quantum energy associated with that mode. And this analogy then gives rise to a bunch of other expressions. And so it turns out that this expression works really well for a lot of cases. But when I got into this field, I was very interested in, again, rethinking it from the beginning. And one of the things I noticed or realized is that this analogy, where you make this analogy between a gas of particles and a gas of phonons, isn't really based on any first principles per se. It's just kind of an analogy that works. And so we got really interested in the cases where it fails or where it doesn't work. And this ultimately gave rise to a very different perspective. I'm not going to go through it. There's a number of papers we've published on this. I think it's decently well established that this approach has merit and can work. What's shown here is that the phonon gas model works fine for a crystalline material where all the atoms are arranged in a periodic fashion. They're equally spaced. They have this regular pattern. Where the phonon gas model starts to break down, as I mentioned, you have these waves that are like sine waves. But when you break symmetry, meaning like, let's say you have an atom that's different, it has a different composition, it's a different kind of atom, or maybe there's an atom missing and you have a defect. These kinds of structures where you now break symmetry, the modes or the different kinds of vibrations no longer all look like sine waves. Now you get things that deviate from a sine wave, and you can get some very strong deviations that look very different than a normal sine wave. And so what we did is we invented a new approach to think about this, where we started with a more generalized description of something like thermal conductivity, which we generally call the Green-Kubo method. And what we did is we decomposed the vibrations into these more generalized modes, which do not have to have the sine wave character. And by generically defining this in a way that's not limited or restricted to sine waves or plane waves, what we got was a result that was more general. And so our approach actually is able to describe not only crystals, it does describe crystals correctly, but it also can describe amorphous materials, alloys, and anything in between, and more generally, any structure that you want. This is important because the phonon gas model descriptions of these kinds of materials, I don't have it here, but do a very poor job of quantitatively and in many cases qualitatively describing what happens in these other kinds of materials. The other case where this shows up is when you talk about an interface. So when you have two materials that are not the same and you put them together, that interface between them, now you've introduced a break in symmetry. So the atoms on the left are no longer the same compositionally or structurally as the atoms on the right. And this is another kind of symmetry breaking thing that then causes the modes of the structure to be different. And what you see here on the right, these are some of the existing attempts to try to describe this using essentially the phonon gas model or the traditional physical picture. What I will have pretty soon, we have some new data. It's not shown here, but we've been able to apply this same basic approach described on the left now to the case of an interface and get much better agreement across the board. Now describing this in a different way, which has at its core, instead of thinking of it in terms of scattering or different particles scattering and bouncing off of each other, instead now we describe it in terms of correlation. And there's really a whole new physical picture that emerged when we started rethinking this problem from the beginning. So this is one really important example of how we rethought the physics from the beginning, and we really came up with a whole new physical picture that does a better job at explaining how heat is transferred through materials in a more generic way. The other key important thing I want to talk about when we talk about atoms, this is the last topic, or one second to last topic I'll talk about with atoms. The other key thing that happens with atoms is that we need, in order to describe the properties of materials properly, you need a good description of how the atoms are interacting. So as I mentioned, the vibrations, or the fact that the atoms are vibrating around some local site, is dictated by the fact that they're surrounded by other atoms. And it's due to the interactions they have with those atoms that ultimately dictates the way that they vibrate, the specific frequencies they have, and the nonlinearities of the way that they vibrate. In order to properly predict the properties of matter correctly, you have to be able to describe those interactions accurately. And this has been a problem that's been around for a very long time. It's been very difficult to solve. What's shown here is just a simple example case of a material that's used inside your computers called silicon. And this is a plot of the thermal conductivity of silicon. So the dots here are the actual experimental data. The black line that you see called DFT, that's from density functional theory. This is a calculation straight from quantum mechanics. This we treat as essentially as the gospel. This is the most accurate approach we have. And the beauty of that approach is you can get this correct. It does it accurately, you get it right. The problem with DFT is computational expense. It's very expensive computationally to do this calculation. And generally speaking, for a lot of the systems and the materials that we'd like to study, DFT is not able to encapsulate a lot of the atoms, like large enough groups of atoms to describe like the complexities of mixtures of atoms, different kinds of structures. DFT struggles to be able to do large enough systems in the amount of time that's conceivable for the computing power we have. So DFT, although great, isn't fast enough to be able to do all the things that we want to be able to do with this kind of theory. So what we do instead is we develop what are called empirical interatomic potentials. These are now closed form expressions, like just an algebraic expression that describes the energy between atoms, that then allows you to describe the forces that they feel as they're moving and as they interact with each other. And what you see here is a plot of a whole bunch of different empirical descriptions for silicon. And you can see that this is log scale. The descriptions vary dramatically, and you get big errors with respect to the description of thermal conductivity. And so although you have all this wide spectrum, you might see one on here, this EDIP 2012, which actually seems to do a pretty good job. It's actually pretty close to DFT. And you would think, well, this must be the best one and does an excellent job. But then when you look at another property, which is called the phonon dispersion, which this is those sine waves I was telling you about, those modes, each of them has different frequencies. This is a plot of, I think of this horizontal axis as representing the wavelength, and then the vertical axis as frequency. This is a plot of wavelength and frequency. We call it the phonon dispersion. And what you see is the dots are experimental data. Again, DFT does an excellent job of reproducing that. But then all these empirical potentials are kind of all over the map. The qualitative description is right because the structure is right. So you get the right kind of shapes, but the values quantitatively are off, and pretty significant errors here. So this is not good. And what this tells you is that even though some of these potentials get close on the thermal conductivity, the way they're describing the vibrations is inherently wrong or incorrect. You've got some major errors. This is another way to see that, is to look at the forces. So if you take the same configuration of atoms, you put them in exactly the same positions, calculate what the forces are from DFT, now calculate what the forces are as predicted by a host of different empirical models. What you see here are very large errors in force. And so you can see tens of percent, 20%, 50%. Here's that EDIP 2012. It was able to get the thermal conductivity close to correct, but the forces are off by almost 50%. Major errors. And so what this says is that it got the right answer for thermal conductivity, but for the wrong reasons. The forces are wrong. And so that's just another material that happens to have the same thermal conductivity as silicon, but it doesn't describe the vibrations correctly. And so this is an important area that we've been working on actually for a number of years, actually trying to improve the descriptions of these empirical interatomic potentials so that we can accurately describe the way atoms move. So one step we made is we actually started optimizing these potentials specifically for phonons. One of the issues with those different potentials that I showed you on the prior slide is that those potentials were not actually like specifically designed just to do phonons. They were actually designed to do a whole host of properties, and it turns out they don't do a great job on thermal conductivity, but they were designed to get the melting point right, the stiffness, and some other properties that are also of interest to physicists and chemists. But instead, we wanted to see what happens if you just want to get the phonons right. And it turns out we could actually make potentials pretty reliably that could get the thermal conductivity right. But if you look over here, the dispersion, still major errors with respect to the dispersion. And it took us a while to figure out what the real problem was. And again, this came from rethinking this problem from scratch. We realized that all the potential functional forms that were typically added to try to correct the dispersion, their functional form inherently was not able to describe what was going on. And what happens is that those potentials use what's called a radial descriptor. They parameterize everything in terms of how far two atoms are from each other. So if two atoms get a little bit closer, the force changes. If they get a little bit further, the force changes. But if they're at that distance, it doesn't matter in the entire sphere of being at that exact distance, doesn't matter where they are relative to each other, it doesn't change the force. And so that has spherical symmetry. It's a radial potential. What we found when we started looking at DFT is that symmetry doesn't exist in these crystals. It's actually not radial or spherical symmetry, but actually certain symmetries in different Cartesian directions. And so we needed a functional form that could actually accommodate that and actually properly account for the fact that if the atoms are the same distance apart, but you rotate a little bit, the forces do actually change. And the radial potentials don't tell you that. So once we corrected that, we ended up introducing a functional form, which we called the translationally invariant Taylor expansion potential, or TITEP, T-I-T-E-P. And we were able to get now this dispersion exactly correct, and we're able to get the thermal conductivity correct. And so this has been a major advancement in our ability to actually describe the way the atoms are vibrating, getting that correct, and also the thermal conductivity, the nonlinearities and the inharmonicity correct as well. One last topic I'm going to talk about on phonons is another rethinking of this problem. One of the things that we got really interested in some years ago is we realized that we had figured out a way to take arbitrary motions of atoms and convert that to the individual modes or the individual vibrations at different frequencies. We could actually decompose that, and we could figure out which modes were active at a given time in a particular group of atoms. And what this pointed us toward is we said, well, we've used this to now study a property called thermal conductivity, which is how well a material can conduct heat. And we said, well, but this approach we've developed is actually more general than that. You could actually study other material properties this way as well. You could study other types of things that involve the motions of atoms and figure out which of the phonons, which of the modes are actually responsible for other phenomena, other types of things that happen in nature. And what we came up with was a concept we call phonon catalysis, because what we realized is that for a chemical reaction, we've demonstrated it here for ion diffusion, but it's general, it should be applied to a variety of different phenomena. When you now can decompose how atoms vibrate into these different modal contributions, now we can look at something like diffusion, and we postulated that when an atom moves from one location to another, let's say you're in a solid, you have a vacancy, so there's a spot where there's an atom missing, and you can have an atom hop into that spot and out of one spot, and the vacancy moves. That process involves certain phonons, and we hypothesized that if we use this modal decomposition approach that we developed for thermal conductivity and we applied it to this, we could actually figure out which modes are responsible for the hopping process itself. And we postulated that if we figured out which modes it was, and let's say it turns out to be a small number of modes, then maybe we could actually do something special, and we could actually purposefully just excite the modes that make it hop and see if we could actually accelerate the hopping process. And it turns out that all of this is true. So it turns out what's shown here on the left, this is a hop, an ion hop in a particular material. Turns out that there's a handful of modes that are primarily responsible for that. This dot showed at the top, this is one mode, that has the biggest contribution to the hopping process. We then figured out how to actually excite just those modes. And what's really fascinating about this is, if you look here, this is now the diffusivity. This is the rate of hopping, so to speak, that happens in a material. As you increase temperature, the number of hops increases. All right, so that's actually going this direction. So this is inverse of temperature. This is typically the way it's plotted, and it generally goes up with increasing temperature. What we've shown is that if you keep all the modes, or the whole material stays at a cold temperature, let's say room temperature, and you only increase the modes that cause it to hop to higher temperature, you will actually get the same diffusivity associated with that higher temperature. And what this keyed us into is really a different physical picture for how chemical reactions take place, how ion hopping takes place. The idea is that you can catalyze the motion, you can catalyze a phase transition, you can catalyze a chemical transition by just targeting the modes that actually facilitate the transition. Those are the only modes that have to get hot, so to speak. You don't need to make the entire material hot. And so this is a really interesting concept that we are working with some experimentalists to try to confirm and demonstrate in other ways. But in theory, what you can do with this is you could have a chemical reaction that normally would not occur at room temperature, and you might be able to excite that just the modes that matter for that reaction to much higher temperature, for example, with a laser or possibly with electrons or some other stimuli. Get those modes excited, and you'll actually see the chemical reaction accelerate, even though the material is still cold. So it might be a high temperature reaction, but it might actually kick off at low temperatures if you excite just the modes that matter. And this is part of the value of doing all of this, of studying which modes, which types of phonons contribute to different things, because it allows us to get access to new capabilities and things that we didn't think were possible before. Now I'm going to completely switch gears and totally switch topics and talk about something very different. So this is now the other side of my work. So finished talking about atoms, and now I want to talk about saving the world from climate change. And one of the most important problems that we have to solve for climate change is what we call the storage problem. So generating electricity with wind and solar is now like one of the cheapest forms of energy generation that exists throughout the world. If you're in a place where it's sunny or windy, it's actually cheaper to put up renewable energy than to put up fossil. But that statement has to be qualified by the fact that that's if you only take the total amount of energy you will get over the full lifetime of that equipment that you install. The problem and the big distinction between fossil and renewable energy is that with fossil, you have a tap, you have a valve, you can turn it on and you can run more natural gas into your turbine and put out electricity, and you can slow it down or turn it off. You have the ability to meter, you have the ability to dispatch the power whenever you want it. And we don't have the ability to do that with renewable energy. With solar panels, you only get the electricity when the sun is out. It's not stored anywhere. With wind, you only get the electricity when the wind is blowing. It's not stored anywhere. And so the only way we can really get to a fully renewable grid where we get rid of all the fossil fuel plants, which is what we have to do for climate change, the way to do that is you've got to invent a new form of energy storage. The problem with existing energy storage, which there are two types, there's pumped hydro plants, there's also lithium ion. The issue is cost. So what's shown here is this is a very qualitative but rough prediction of what fraction of the world's energy can you have come from renewable energy as a function of the cost of the energy storage that you have access to. So if you look at the cost of lithium ion, we're down here. This is the current penetration of renewables at about 25%. And if you can decrease the cost of energy storage, you can see that we can get to much higher penetrations of renewables. And basically the key point is that the decrease in cost we need is not a factor of 2. It's not a factor of 3. It's more than a factor of 10. Like we need a dramatically different way of storing energy in order to get to much lower cost so that we can facilitate full penetration of renewables. Lithium ion batteries are cheap enough for cars, but cars is a very different application than storing energy at the grid scale, where we're talking about the utility grid, which is thousands of times larger than what you need in a car. Now, when doing this, there are a couple important key parameters that come out of all of this. Most notably, there's a property we call the cost per unit energy. This is the cost of all the equipment that you need to buy and install that stores energy. There are different kinds of technologies for storing energy, and some of them can be separated into different components. You also have to pay separately for the power that you use to charge it and discharge it. There's certain equipment in an energy storage system that's associated with the rate at which you charge and discharge. Another key term is called the round trip efficiency, or the RTE. This is you put in, let's say, 1 joule of electricity, you will get less than 1 joule back out. What fraction that is called the round trip efficiency. And the last is the lifetime. Lithium ion batteries don't last as long as we need them to. And so how long the particular system, energy storage system, can last is another key piece. So there's a number of studies listed at the bottom left here that have actually all reached similar conclusions. One of the major things that's a bit non-intuitive that came out of this is that the cost per unit energy is actually one of the most important things. You need to be able to store the energy very cheaply, even if it means sacrificing something like round trip efficiency. The round trip efficiency, surprisingly, can actually be pretty low and still be cost effective. And this is one of the big realizations that then led us to start thinking, well, if I don't have to worry so much about efficiency, maybe I can store the energy as heat, because storing heat is one of the cheapest ways of storing energy. This ultimately led to this concept that we're pursuing now in my company. We call it thermal batteries. I'll describe in concept how it works, and then I will try. It's going to sound like science fiction. Then I'm going to show you some videos and try to convince you that we actually can do this. It works. So the way we store electricity is we take electricity and we actually run resistive heaters. And that may sound like a dumb idea. If you have taken the thermodynamics class, one of the dumbest things you would want to do is we spend so much effort going from heat to electricity the first time to now go from electricity back to heat, only to pay the second law penalty a second time is a really bad idea. But the only reason we do this is because the cost of storing heat is so cheap. That's the only reason this makes sense. So we take in electricity from renewables and we run resistive heaters. These resistive heaters are basically the same as an incandescent light bulb filament. So this is glowing white hot. at around 2,500 degrees Celsius. So this is similar temperature to an incandescent light bulb. The light coming off of that heating element is then transferred to a piping network that we make out of graphite. So we make an entire system out of graphite plumbing. We've got pumps that are made entirely out of graphite, and inside these pipes is a liquid metal. It's liquid metal tin. Think of it like solder. It's similar to solder. It melts at a low temperature, around 232 degrees Celsius, and then it boils. It doesn't boil until 2,600 degrees Celsius. So we have a huge liquidous range that we can work with. The liquid metal comes in at 1,900 degrees Celsius, and it doesn't leave until 2,400 degrees Celsius. That then gets pumped over to these storage blocks. These are made out of graphite, so again, more carbon. As the liquid metal passes through these pipes, it heats up the graphite to the peak temperature of 2,400 C. And when that happens, the thermal battery is now fully charged. These blocks of graphite are thermally insulated from the environment, and the whole thing is housed inside of an inert environment where we build a warehouse around it and fill it with argon gas so that the materials, the graphite and the tin, do not oxidize. This energy can now sit in these blocks for months. When you're ready to now get electricity back and you discharge it, you pump the liquid metal through, you turn the heaters off. So now you're going to use these blocks as a ginormous heater with a bunch of thermal mass that can hold all that energy and keep the liquid metal hot for a very long period of time. When the liquid metal comes out, it then goes over to what we call the power block. This is where we convert the heat back to electricity and put electricity back on the grid whenever you want it. One big departure that we do, unlike what you would normally think to do, if you want to convert heat to electricity efficiently, the best way to do it is with a turbine. We do not use a turbine. We actually use solar cells. We actually use multi-junction photovoltaic cells that are essentially thermal photovoltaic cells that instead just convert the light coming off of the piping. This whole thing is so bright. There's so much light coming off of it. We make little furnaces that are fueled by the liquid metal. And then each of those little furnaces has a stick of photovoltaic cells that are water cooled, that are dipped down into this extremely intense light to now retrieve electricity and put it back on the grid. One of the real important and cool features of this is that those PV cells on that stick can be actuated. They can actually be dipped into the light or pulled back out. And this is one way that we can modulate the output of the device. The PV cell cooling is cooled by water, and then that's then dissipated in a dry cooling unit, which then goes outside. The big question with this is, why is it cheap, right? So the way this works, just to walk you through the basics of why it's cheap, just walk through these basic economics here. The graphite we're using to store the energy, it's about $1 a kilogram. Divide that by the heat capacity and the temperature swing. We're swinging from 1900 C to 2400 C, so it's a 500 degree swing. And then the round trip efficiency for our system is about 50%. So when you do all of that, it turns out that storing the energy this way comes out to $7 per kilowatt hour. Compare that with the cost of lithium ion batteries, which is up at around 100 to 200, or really like $300 for system level costs. And you can already see that we're more than 10 times cheaper. And this is where it gets really interesting, is the fact that we can make this so cheaply. So it's all about cost. Even when you now add all the rest of the infrastructure, which actually dominates the cost. So the core medium is, a significant part of the cost. That's the graphite cost here. But the rest of the system is actually the majority of the cost. But even when you add all that, it still comes out just around $25 a kilowatt hour. When you add up all the power components, it comes out to about 60 cents a watt. By comparison, when you ask, why don't we use a turbine instead? Number one, the turbine we need doesn't exist. And number two, this is actually cheaper than a turbine. Turbine's about $1 a watt. This is coming out around 60 cents a watt. So it's a significant savings actually doing this photovoltaics approach. Now, the next question you should ask is, that all sounds like nice science fiction, but what makes you think you can do it? The big question that we tried to answer first, and we had an initial ARPA-E funded project, this is really what opened the pathway for so much of the things that we're doing now, is how you're going to pump it. So I mentioned we have mechanical pumps pumping liquid metal. This was, again, this was one of those things that when I mentioned this idea to colleagues, was met with great resistance and disbelief that this could be done. Why? Because the materials that you're using for the mechanical system are brittle. The typical thing that you do when you want to build a thermal fluid system, generally speaking, no matter where you go on Earth, you will see that these systems are all made out of steel or nickel alloys, generally speaking, all made out of metals. And for good reason. We like to use metals because, number one, metals are ductile. They fail gracefully. They don't just snap all of a sudden and fail catastrophically. And number two, they can be welded. So you can actually make a permanent joint that doesn't leak, and you can rely on that joint. When you talk about ceramics, you start talking about graphite, you can't weld them. They're not materials that can be welded. And so, and they're also brittle. And so this is where a lot of the skepticism that this could actually work came from. Long story short, we figured out how to make it work. And this is a video of us pumping liquid metal at 1400 C for the first time. This ended up in the Guinness World Records. This has also ended up in a Nature paper. And this really kind of set us on this path of demonstrating a whole new way of moving heat at extremely high temperatures that had not been possible before. 1400 C, the temperature we're here at this in this video you're looking at, steel would be liquid at these temperatures. Nickel alloys would be liquid at these temperatures. And so you cannot make an infrastructure that goes this hot with conventional metals. The second big push we made was these solar cells. So when you talk about solar cells of this type, we typically call them thermal photovoltaic cells, or TPV. Thermal photovoltaic because the source of the light is a thermal source that's terrestrial, it's on Earth. It's not the sun. And if you look at the history of the efficiency of these devices, it has not been very good. I actually looked at this technology when I spent some time as a fellow at ARPA-E back in 2012. So back around this time, I was going and looking at the literature. I saw these efficiencies down here around 10, 20%. I didn't think it was very compelling. And I had written the technology off. I actually thought that this would never be high enough efficiency to ever matter. And later on, when we started rethinking this, re-looking at it again, we noticed what was really the big gaping hole. And it's really a combination of using extremely high temperature heat source, higher band gap cells, and making use of all the high quality material developments that actually happened over these years. When you employ all that, we actually set a new world record up at 41% efficiency. So we got a second Nature paper on this, setting the world record on TPV efficiency as well. And we have a path to get to the 50% that I mentioned was our target round trip efficiency for our thermal batteries. There's another set of improvements we plan to make to the cells that should get us there. So I'll skip through the rest of this pretty quickly, but this high efficiency is not just at one temperature. It actually works over the range of temperatures that we're interested in. And this is really what sparked us to go start the company, because now we had a device that we could use that broke the threshold of being better than a turbine. So the average turbine efficiency in the United States is about 35%. And so at 40%, we're better than that. And so now this actually gets to a range where it's pretty interesting for starting a company that could make some money. We have done this in the lab. I'll thumb through a lot of these pictures real quick. These are some of my students assembling some initial testing that we did with a lot of this, where we actually build systems that operate above 2000 degrees centigrade. This is graphite insulation. So when you get this hot, the only kind of insulation you can use is actually made out of carbon. We've actually built these kinds of things and put cells in these kinds of hot environments. There's another really interesting issue that showed up that we've solved. We have a patented solution to this problem. When you put a water-cooled, it really doesn't matter what it is, but something, let's say at room temperature inside of an environment, a few inches away from something above 2000 degrees C, what you just made is actually an evaporator, right? So the hot side is so hot that it'll partially sublimate, and that sublimated material will deposit onto the cold thing. And so this is a huge problem for PV. If you put a PV cell in this hot environment, it's just going to get coated with graphite and turn black. And this happens within minutes. So this is actually a really important issue. We have a patented solution, which is basically we blow gas over the PV cells. So because I teach heat and mass transfer, it was kind of an obvious solution for me. Once I realized that this was the issue, one immediately innovative approach you can take is actually to blow gas over the cells and sweep away the material that would deposit before it has a chance to. We developed a rather complicated rig to demonstrate this with PV cells and gas flowing over it with coolant delivered. We also use tungsten as a lower vapor pressure medium that's doing the emission of the light. And long story short, it works. This is now data showing PV cell performance after 6 hours in the cavity and no change in performance. And moving on quickly, I'll just say, what's next? I've started a company. We are now building this same technology. We actually have a whole kilowatt hour prototype in my lab that works. What we're now doing is scaling that up by essentially a factor of 1,000 in terms of energy and power, doing a 1 megawatt hour pilot demonstration. If you ever have a chance to go to the company website, you can see a full explainer video that walks through how the technology works, shows you some interesting visuals of what it would look like at much larger scale. And we are building this now. We're working out of a MIT Bates facility, which is 25 miles north of MIT. And we have a whole team of engineers that are working on putting this together so that we can demonstrate essentially all the components at the same dimensions and operating conditions that they would operate for a gigawatt scale plant. But we've now modularized it so like the pumps, the valves, the piping, all these individual components, we can test a smaller array of them at a smaller scale, prove that they work, and then after this, all the installations we do will be the same hardware that we qualify in this first demonstration, now with larger arrays, hundreds or thousands of these components now replicated, but it's the same components, the same pump that we're demonstrating, same valves, same blocks, same piping, all these components all together. So with that, I'm going to move on to the last topic, which I'll do in just a few minutes, just to tell you quickly about this other technology that we are working on. This is methane pyrolysis. So once we figured out how to pump liquid metal at extreme temperatures, we then realized that there's other things you can do with this beyond just energy storage. And one of them is actually to make hydrogen. So hydrogen is necessary. I know people a lot of times talk about the hydrogen economy. That's a lofty goal, but we need hydrogen to survive as human beings because you need hydrogen to make ammonia. You need ammonia to make fertilizer so you can feed 8 billion people on Earth. So we make hydrogen today. This process shown on the left. This is called steam methane reforming. It's also followed up by something called the water gas shift reaction. The two of those things together, we'll just call it generally SMR. The way you get hydrogen is you take methane, you take natural gas, you react it with water. And so what happens is the oxygen in the water wants to pair with the carbon, and all this hydrogen comes off as hydrogen gas. So you first make CO, then you react the CO with water, get CO2. And so this process fundamentally, from a thermodynamic perspective, requires the creation of CO2 in order to get hydrogen. And so this is responsible for somewhere between about 1% to 2% of global CO2 emissions, is just making the hydrogen we need to eat. And there's another process that you could do, which is instead, what if you took that methane and you just heated it up so hot that you pass the realm of its thermodynamic stability and it actually decomposes into solid carbon and gaseous hydrogen. And this is called direct thermal pyrolysis of methane. This is a cool approach you could take. It doesn't make CO2, it now just makes solid carbon, and the amount of energy required is less if you can contain it, if you could figure out how to do this. And so this is the approach that we've been taking, is we actually have a reactor that uses liquid metal tin, same infrastructure made out of graphite and liquid metal that I've talked about for energy storage. And what this does is we take methane. We have a container of liquid metal. We bubble up methane through it. So as the methane bubbles are rising, they heat up to the temperature of the liquid, which is, let's say, 1400 C. Inside the bubble, the reaction gets carried out, and you get a little carbon particle that's formed, and hydrogen gas comes off the top. And what you end up with is a bunch of carbon that would float on the surface, or we've actually found a lot of it actually will go out with the hydrogen gas, and you can separate it. But the key thing is the plugging problem. And so what typically happens, you might think, well, why don't I get rid of the liquid metal? I just put this in a tube, I heat up the tube. If you have this reaction happen inside a regular tube with no liquid metal, what will happen is as the reaction happens, that carbon will coat the surfaces of the tube. Very quickly, it'll fill the entire cross-section and plug the reactor and choke itself. And you'd have to shut it down. And this would not be a cost-effective way of operating it. And so the key thing is, how do you continuously remove the carbon? Real quick, the economics of this approach are very, very attractive. It's primarily dominated by the cost of the methane and the electricity. When you go to large scale, this actually can get cheaper than the steam methane reforming process. So it's super exciting in the sense that if you can actually sell the carbon, which we think you can, If you sell the carbon, you can actually reduce the cost, the break-even cost for selling the hydrogen, and you can get to significantly lower costs than steam methane reforming. I'll skip through this pretty quickly and just say that we have a reactor in my lab now that does this, so it works. This is a version of it that shows the liquid tin at about 10 inches. We bubble up the methane through it. We get hydrogen that comes out. We've made essentially pure hydrogen. And this is the carbon that we get out. It's not carbon black. I don't exactly know what to call it. I could show you SEM images of it. It's strange, it's different. This video shows you what it looks like. We call this the carbon snow globe. It has a very high surface area and falls slowly through gas, which is actually why most of it gets entrained with the hydrogen gas going out and gets carried out. So with this, I'm going to stop here. Don't want to run over time, and I want to give great thanks and gratitude to all the agencies that have funded my work, all the graduate students, postdocs, research scientists that have contributed to this work over the course of a decade or more. And be happy to take any questions that you have, and just really appreciative for all the support from NSF and otherwise.
Thank you very much for your inspiring comments. And also, I think it's a rare investigator that is in the Guinness World Book of Records multiple times, and I think there are more of those to come. I'm going to hand it over now to Dr. Sumantra Acharya, who will be moderating the question and answer session here today. Dr. Acharya is Program Director in the Directorate for Engineering here at the National Science Foundation in the Division of Chemical, Bioengineering, Environmental, and Transport Systems, and he manages the Thermal Transport Processes program. Sumantra?
Thank you, Susan, and thank you, Dr. Henry. Thank you, Asegun, for being with us today and for delivering an outstanding lecture. I mean, so going from photon transport to all these user-inspired end-user applications is truly inspiring. I also want to thank the audience. We have a large number of participants today, nearly, from what I count, 160 people. And I really want to thank you for staying tuned to this outstanding lecture. So as a reminder, today's presentation was the first of 3 in a series from this year's Waterman awardees. We have included a link in the chat to our events pages with more information about the upcoming talks. For NSF staff, there will be a post-lecture discussions with Dr. Henry starting at 2:10 p.m. So please join the Zoom link if you have further questions for our speaker at that time. So I guess we're going to come back around 2:10 p.m. Mary Kay, is that correct? And
actually, we're going to take Q&A from the audience right now, the public audience. It's in the Q&A box right now.
Okay, sounds good. All right. So for the public audience, if you have any questions, please put it in the chat.
Yes, if you click on Q&A, you should be able to see the questions.
Right.
I can start. Is the water used for cooling part of a closed loop system? Where is the water coming from? That's from Ronan Selby Quran.
Yeah, that's a quick answer. The short answer is yes, it is closed loop. This doesn't have to consume water. There are a small bit of gain you can get if we use a water-based cooling system that's open loop, or a cooling tower, for example. Maybe if we site this at a place where you have an existing, or let's say decommissioned power plant, we could make use of the existing cooling infrastructure. There's a bit of gains that happen there, but everything I've shown you is actually spec'd in terms of dry cooling. So we assume you can put it anywhere on Earth. You have an initial charge of water that you have to supply that you can carry to the site, but it's not much, and then everything stays closed loop.
Okay, from Ben McCall, thank you, Asegun. From Ben McCall, impressive work. How are the graphite joints sealed in your system?
That's a great question. So this is, in essence, quote unquote, the secret sauce. I will try to describe it in a couple ways. We have some patents on this. The basic way it works is there's one kind of there's 2 materials involved. One was invented quite some time ago. It's called graphite. It's a commercial form of carbon that's actually flexible. So you can buy all graphite packing ropes. You can buy gaskets, flexible gasket seals. And what we do is we essentially bolt things together and we squish down on a seal that's all made out of carbon, and has one of the things I didn't talk about. Our choice of tin with carbon is important because tin and carbon have no chemical interaction whatsoever at any temperature. So we have no corrosion in our system. So we bank everything out of graphite. The second material of interest there, actually, I mentioned you can't weld graphite, but you can do something kind of similar, which is you can reaction bond graphite to itself and even to other materials. So there are reaction bonding agents that actually cure at pretty low temperatures, like in a toaster oven, where you can basically add a material that's essentially, let's call it, we like to call it Nutella. It's kind of the consistency of Nutella. You paint that on a joint, you can do an overlap joint, cook it at toaster oven temperatures, and what's left behind at the end is actually only graphite, and you can form a graphite to graphite joint that's permanent that way. So we've demonstrated all these various things, and we're now just demonstrating at a much larger scale. But that's the basic way that we make the seals.
Thank you, Asegun. Another question from Ronan Selby Curran. Are rare earth metals always required in order to build existing energy storage systems, pumped hydro plants, and lithium-ion batteries? If so, how do the impacts involved in acquiring these rare earth metals compared to using fossil fuels?
I think the short answer is no. Rare earths are not always required. There are a number of energy systems that people have developed that do use rare earths, but it's by no means a requirement. In fact, it's one of the key tenets that all the companies, all the groups that are working on low-cost energy solutions tend to have as like a starting point as we try to avoid the use of rare earths. In our case, we don't have any rare earths, so we're just using tin and graphite. Almost the entire system is made out of carbon.
Okay, thank you. Question from Madeline Green. What is the lifespan of a graphite pump?
Great question. So graphite pumps are actually already made commercially. They use them in the metals industry. Those pumps actually operate in air, and so they change out their pumps or change out impellers in the order of like every 3 to 6 months. In our case, we expect to be able to operate, tens of years with our pumps. And the reason is, number one, we're not in air, so there's no gradual oxidation of either the graphite or the metal that it's contacting. Our system is much more carefully managed in that respect. And then the second thing is, one of the main things we're doing now is we're actually trying to demonstrate our system and specifically the bearings. So the bearings, we actually want to be lubricated in a way that actually prevents them from having solid-solid contact. And so we are basically designing every aspect of our system to have like 30-year plus life.
Great. Question from Muna2 Bell. Are any of the materials developed biocompatible? For example, carbon?
Yes. So I would say this way, we haven't really developed any new materials, so I'd have to conduct the consult the MSDS for each of the materials we use. I mean, yes, carbon. So almost our entire system is made out of carbon. What qualifies as biocompatible? I would have to. It's not my area, so I'd have to learn what the specific requirements are to technically qualify something as biocompatible. All the stuff that we're using is safe to use. You can pick it up. There's no danger. It doesn't have any toxicity. But I'm not sure what is actually the threshold to call something biocompatible. But to the extent that carbon is, then yes, almost the entire system is made out of carbon. The main two materials by mass are or even volume, or carbon and tin.
Question from Trevor Clark. Is it possible to say what the phonons in the liquid metal are doing? And can phononic tuning be done with the liquid metal?
So this is maybe somewhat of a bit of a subtlety in what I was saying. Part of my early discussion about phonons was centered on the idea that the atoms are oscillating or vibrating around a fixed location. That's in many ways how phonons are defined, meaning the atoms have to be localized to one location, and you have to have vibrations, which now allows you to do a decomposition of how those vibrations stack up. When you're talking about a liquid, the atoms are not vibrating around fixed locations. Instead, they're actually gradually drifting past each other. So the notion of a phonon isn't actually a very well-defined concept for a liquid metal. You could do a solid metal that way, but once it's liquid, the whole concept of phonons kind of falls apart. There are descriptions where you temporarily can describe a system as having phonons or short-lived phonons, but you can think of it maybe as the phonons live for a little bit while they're vibrating, and then the phonons change as they drift. But generally speaking, we don't tend to think of it as phonon transport in liquids.
Question from Pei Zhang. What is the overall efficiency of your whole process of converting electricity to heat and converting heat back to electricity?
Yeah, so the round trip efficiency we expect to get to is 50%. And so that's actually where the photovoltaics are actually a little bit above 50%. And you account for a little bit of loss, less than 1% or so loss going from electricity to heat in the electronics. The big law, then there's a little bit of heat leakage from the insulation of the hot blocks. That's 1% or so. And then the bigger hit, the huge hit you take is on the thermal photovoltaic conversion, which is the 50% coming back out. So it's largely 50%. It's a little bit higher than 50% for the conversion of heat to electricity, but then when you account for the other couple of losses you take, it's expected to be around 50%.
Another technical question: due to high temperature requirement for storage, how long can the storage material last without degradation?
Great question. So how long a material can last, or what one considers high temperature, is actually relative, right? So one of the useful points of comparison is a material's melting or decomposition temperature. So if you think of, let's say, our peak temperature, 2400 C, and now compare what that is relative to the decomposition temperature of graphite, which is well over 3000 degrees C, like 3500 degrees Celsius. Graphite at 2400 C is akin to like steel at 700 C. Interestingly, unlike metals, metals get softer, they get weaker as you go higher in temperature, pretty monotonically, they just always get weaker. Graphite is interesting because graphite actually does the opposite. Graphite actually gets stronger from ambient to 2600 C. It's not a lot stronger, but it's actually going up. It doesn't get weaker, it actually gets a little bit stronger. So we anticipate that our system will be able to survive 30 plus years because there's not really any inherent degradation mechanism. There's no corrosion. The only, I guess, degradation you might be able to say is like creep or something over time. So there is a creep rate, but generally speaking, we design creep rates, of course, vary exponentially. And so our system, all the dimensions are designed so that our stuff can last well beyond 30 years, like 100 years or more before you get like 1% or 2% of overall growth or shrinkage due to creep. So generally speaking, we're designing our system to have an extremely long lifetime.
Thank you, Asegun. There's a non-technical question here where Lane Fargo Navarro, she says, he or she says, Dr. Henry, I was very interested in your opening comments about your childhood and getting interested in science and engineering. I work for a nonprofit that focuses on getting kids interested in STEM, especially minorities. Would you be willing to talk to me about your experience on another occasion?
Definitely.
So
should be easy to find my email online at MIT. Send me an email. And please remind me that it was from the Waterman lecture, so I'll catch it.
So just as a reminder to you, Asegun, the last name is Navarro if you get an email.
Got it. Thank you.
Another question that has come in, it says, related to the first part of your talk, on a macro scale, the diffusion model is used for heat transfer. Is there a small is there a small enough scale in time and space where a wave equation is relevant, or is this one of the areas where analogies to other physical systems break down?
Okay, one more time. Can you repeat the question?
So basically, the question is that on a macro scale, the diffusion model, the heat conduction model is used for heat transfer. The question is there a small enough scale in time and space where the wave equation or the phonon transport equation is relevant? Or is this one of the areas where analogies to other physical systems break down?
Got it. In short, the answer is yes. There is a scale. There are a couple different things that happen as you go down in length scale. So if you, for example, measure the thermal conductivity of a solid material at low temperatures, typically what you'll find in a crystalline material, typically what you'll find is there's a peak. So it starts from effectively zero thermal conductivity. It quickly rises up. There's a peak, and then it gradually comes down, typically with like 1 over temperature behavior. That peak, the height of that peak and where in temperature that peak occurs is actually a function of the structure of the material, like the size of the grains. The reason this happens is because the first length scale you usually encounter as you shrink down is a limit on what we call the mean free path, or the limit on the distance that these waves can travel before they run into something. So once you go below that length scale, you usually have to make some modifications to the equations you use. Very often, it turns out that you can just make a modification to the thermal conductivity itself, and the diffusive equations will still work. There's another barrier or threshold you'll cross if you keep going down in length scale. Eventually, you can get small enough to where the actual wavelengths of the phonons are truncated or affected by the size of the material. This is typically tens to less than 100 nanometers. Once you get that small, now you get another effect, to your point, where other kinds of expressions, other kinds of descriptions for how heat transfer happens, again, need to come into play. There is also another impact, I think, which is relevant for what was being asked, which is, since heat is transferred through these vibrations, there is an intrinsic limit on how fast a signal of a thermal disturbance can transfer through a material, which is limited by the speed of sound. So these waves are actually the same as you go to the zero frequency limit. They become the same as sound waves. And so if you start heating a material on one end, the material on the other end, it's impossible for it to know that heating started until at least the speed of sound is able to transmit over there. So there are a variety of other kind of modifications to the regular diffusive equations that account for these effects, and those things can be included in the model.
Okay, I think this is, we're reaching the end of the time, and I think so I will stop the Q&A from the general community at this point in time. Asegun will give you a little break. You've been talking for almost an hour, and we'll come back at around 2:10 for you to talk to the NSF staff. For the
Sounds
NSF staff, you have a separate Zoom link in your calendar invite to join the post-lecture discussion at 2:10 p.m. So once again, Professor Henry, thank you for the very inspiring lecture. So I think the potential applications are huge, and we look forward to your making that impact. Thank you.
Thank you. Thank you for everyone for coming, for listening, and I appreciate all your attendance.
Bye. Thank you. Thank you all.